Okay, so what I'm going to do is I'm going to look through these probably later on, well, probably not later on tonight, sometime during the day tomorrow, and I want to go and compare them to what some of you have been submitting. If you checked out the grades for the last programming assignment, they weren't good, and it had very little to do with whether or not accurate solutions were submitted. It had much more to do with solutions that completely matched another student's solution, which, you know what, at the end of the day, I don't necessarily care that much about that. If you guys work together and you learn from the stuff, that's fine. But you're submitting solutions that aren't using things, like not even close to things we've done in class. Like array lists and maps and all sorts of stuff. So is it possible that you know how to do that stuff? Sure. But from my perspective, it looks like code that I didn't teach you how to write. And seeing as though I've made a pretty big deal about using only what we do in class, blah, blah, blah. And, you know, frankly, if when I say it, I'm a pretty loud, clear speaker, I think. Okay? So if I'm saying it and you give me the whole head bob thing and you don't actually understand me, then I guess that's on you. But, you know, punchline is that I wrote a note on there, you know, and I, you know, for something that even looks correct, but is using a whole bunch of stuff that we never talked about, that's not worth points. It's not like it's worth some points off. It's not worth points because I'm not convinced that's your work. And it's not because I just want to be a jerk grader. I want you guys to learn something, but you have to prove to me you're learning things, right? You know, and as I flip through these, a couple of you obviously know exactly what's going on, or at least it's very obvious to me that if given 5 or 6 hours to sit there with some resources and things like that, you could put together a homework assignment, right? A couple of these, you basically copied what I wrote on the screen there. So that's showing some pretty deep incompetence. So that was one problem with the homework assignment, and it really has nothing to do with the quality of the actual solution. It has everything to do with your inability to follow directions. You know, if I say do an assignment and do it using only things we've done in class, why don't you? This is the punchline. You know, and then I get the sob stories in the emails like, oh, can I turn this in again? Like, well, you have the solution from last week. Why am I going to waste my time watching you turn my solution in? You know, you got to do the work right the first time. And, you know, I hope you guys realize I'm not purposely just trying to punish you. I don't like giving bad grades. And I want you to work hard. I want you to struggle with the stuff. And I want to be able to reward you for hard work, even if it came up a little short. But when you're just turning in stuff that's either obviously not your work, or if it is your work, you're just not capable of following directions, that's problematic in and of itself, right? So,
but it's okay to use something from last semester, right?
It's okay to use some things that we used from last semester, but if you're in doubt, I mean, you know what, as I go through there, the things that I'm giving zeros for are not things that are like borderline. You know, it's not like, oh, well, did we use this last semester or not? If I'm questioning it, I just look past it. It's not a big deal. You know, like string tokenizer, did we use that? Maybe, maybe not. Well, that's fine. The stuff I'm seeing is like, you know, fairly complex, like generics, which we've never talked about. And my gut feeling is if I ask you, I'm thinking it was like 4 of you, what a generic is. You couldn't tell me. Okay? If I gave you a quiz right now, asked you to tell me what generics are in Java, would you agree that you probably couldn't tell me? Okay? Like half of you submitted assignments that use generics. So, you know, hopefully you see I'm mad, right? You can see that? Yeah, because I don't get mad very often, you know, I want to see you guys do well, but I mean, grading the assignments was just infuriating, and you know, usually, you know, I just get upset with the papers, and that's more to be expected. I've spent quite a bit of time talking to you about the writing stuff, but I expect your writing to be on the weak side. So I try to grade you hard on it, and then I curve a little in at the end because I want you to be rewarded for trying to improve. Hopefully what I see is over the 7 writing assignments that for those of you who struggle, your first couple were, mediocre, but then all of a sudden you started seeing you learning from it. And if I see your last couple of writing assignments are great improvements over your first couple, I'll just go back and give you points. That means the mission was accomplished. You learned something, right? You got better at writing. That's the whole point of going to college, right? But to be honest, as I look at some of the programming assignments, it really seems like the point that you're going to college is to keep your student visas or something like that. It sounds rude, but it really, based on the crap that I'm seeing turned in, it really feels like that to me. Bottom line is I'll look at this, and if I am convinced that based on what you did on this, that what you submitted in the homework may have been your own work, I might consider doing something about it. At the very least, I'll make a mark on it moving forward so that if you can start following directions and doing the work in terms of what we've done in class, I might go back and fix some old bad grades if you can prove to me you could start following directions. Okay? But punchline is still going to be, if I look at this and I look at your assignment and it's filled with crap that just is beyond you, what does that tell me about your character? Right? If you're struggling with stuff, you should be asking questions. How many of you think asked me questions this past week? One person. Actually, 1.5 people. He's short. He's kind of short. Okay. Right? And not very many. So a majority of you didn't ask questions. And frankly, the people who did ask questions, I think, did all right on the homework. At least generally speaking. I've been teaching for a while. It's pretty easy to detect when somebody's BSing you. You know what I'm saying? So I don't know, maybe you can squeak it by some of these other teachers or something like that if they're, been doing this a little bit shorter periods of time. But, and now the funniest thing this week, hopefully it's some of you in here because then you'll find it even funnier. The stuff with, so we have this new self-assign thing, right? Oh, that's the most infuriating tool, period. That shows me all the stuff that in the past I've missed, right? You just copy crap off the internet. So, so self-assign gives me it shows me in your papers mostly, although I have it turned on for the programs too, just so I can see where it's literally identical to somebody else, so I can at least look closer. If it's 2 people who've worked together and they've used stuff from class, I don't necessarily care. But the papers, the self-assign assigns a percentage. What percentage of the paper was likely stolen, right? And the thing is that most of you go in and when I ask a question on the papers, you copy my question in there, so that's obviously going to get flagged, and that's not against the rules or anything like that. So percentages in the 50% are not really that big a deal. But there's a whole bunch that are clearly like 100%. But what's been funny in some of the other classes I've been talking with the other professors is the students are becoming wise to self-assign. They're learning ways around it, but they're doing it in ridiculous ways. So as they run the report and they see the report that self-assign gives them, they're using thesauruses to change words so that they get a lower percentage, right? Mm-hmm. But some of the words they're changing aren't like they're changing people's last names and stuff like that. Yeah, like there was I think an author or something, like his name was like Rivers or something like that. Okay, and they changed his name to Stream or Rain or something like this. It's like if these students spent half the time doing the work that they do trying to cheat on the work, I don't even get it.
I just saw when I was in China, there's a thing that when they are writing papers, also just like deliver papers to homework, and in order to prevent from, they say they're copying this entirely, so they just put some period randomly, or just change the line. Mm-hmm. Switch the space place like maybe they speak this line, for example, they turn it into ahead of another line, then or just add something weird between then to escape from.
Mm-hmm.
They say then because software they say it's not identical. So,
Right.
So
Yeah.
it maybe there is doing it, but they're just
So
bad way.
So here's my I guess my plea, but my offer. This is more of an offer, I think. So a majority of you basically got caught cheating last week. It's the punchline. I'm not going to go turn anybody in. They're not going to mark that down anyways. I don't care. Okay. Punchline is I want you to learn from it. So, if you cheated, you cheated. What I want to see you do is don't go back and redo the work. We already did the solution. The rest of this semester, the rest of this class, I want you to take pride in your work. If you have questions, ask questions. All right? If you're questioning whether or not you are allowed to use something, ask. I'll clarify. Okay? Almost every single time I'll say, yes, you can use it if you ask, because that pretty much proves you know how to use it, right? Okay? But what I'm going to do is if from this point forward, you can actually show me that you guys can be good students that take pride in your work and don't just look for the cop-out, I'll go back and try to fix some of these old grades. Well, I'm not going to let you resubmit work I've given you the solution for, okay? But at some point, you got to show me a little ethics here, especially since our first class you have to take is ethical computing, right? I mean, come on. You're not going to be able to cheat your way through life. So for all you that got zeros, which is a lot of you in here, take it as a wake-up call, take it as a scare, do better moving forward. And I'll do what, and if you can do that for me, I'll see what I can do for you fixing some of those low grades. Sound fair? Okay. But don't turn in more cheating stuff because my grace is going to go down quick. A couple of you have known me for a while. I rarely get angry. Very rarely. So, yeah, I guess pretty disappointing. But having said that, that's a done deal. So, let's reboot and move on with our assignment and then talk about what we're going to talk about next. All right, so homework was, we were doing binary trees and it was what, patient records? Okay, and a patient was what, a name, first name, last name, age? Okay, and then they got added to the tree by age?
85.
Say this again?
5 years.
5 to 85.
Oh, 5 to 85 was the range of years, okay. And then they get added to the tree, and we order the tree by age, right? And then you were supposed to print out whatever was the youngest person, whatever was the oldest person, and then the root, right? Kind of proving you can traverse the tree. All right. So let's look at this. I have a project. So let's call this guy CSC537, fall 2015. What? Patient tree, you think? Patient tree? Close enough-ish? All right. So let's go ahead and create our driver. All right, so let's start off by creating some patient records. So we need to give ourselves a class for the patient record. So yeah, we'll just call it a patient, or I'll call it patient record. Good enough. All right, so here's a patient record, and a patient record is going to have a private string F name, private string L name, and a private int age. And then we'll have our constructor for this guy. And the constructor is going to take in a string first name, string L name, and an int age. And we'll say this dot F name is equal to F name, this dot L name is equal to lname, and this dot age is equal to age. All right. And then let's just go ahead and give ourselves a little display method for a patient record. So let's say public void display, and we'll say system.out.println patient concatenated with this dot fname space this dot lname space age this dot age. All right, so that's going to display that guy. So let's go ahead and just generate a bunch of patient records to prove that that piece is working before we build our tree for holding these dudes. So we're going to go ahead and we're going to say for int I is equal to 0, I is less than, did I say 100 patient records or?
Yeah, 100.
100 patient records. I plus plus, and let's go ahead and just give ourselves a patient record array called the patients, and this guy's a new patient record array of size 100. We'll go through here. We're going to need to something to randomize ages, right? So we'll do random r is equal to new random, and this will import java.util. All right. So we're going to say the patients at bucket I is equal to a new patient record. And this guy is going to take in a first name, a last name. So we're going to call the first name is going to be A. Last name is going to be, actually, let's do it this way. First name will be patient. Last name will be the string version of I. And then we'll do r dot next int. And you said 5 to 85?
Yeah.
All right. So we're going to say 80. That should give me 0 to 79. So we'll say 81 plus 5. All right, so we'll create a new patient record whose first name is patient, whose last name is like 0, 1, 2, 3. So we'll have patient 0, patient 1, patient 2, patient 3, patient 4, those guys. Okay, and then we're going to go ahead and we're going to give him a random age. So r.nextInt 81 will give us an age between 0 and 80, plus 5 will give us an age between 5 and 85. Make sense? Okay. So that is that. So now let's go ahead and, well, here, we'll just print them out while we're going through that loop for right now. So right afterwards, we'll say the patients at bucket I dot display, and we should see 100 patients with hopefully some random ages in there. All right, so look reasonable enough. All right, so we got our patients. So now what we want to do is we want to go ahead and start putting these guys into a tree. Well, in order to do that, we're going to have to build a tree capable of holding patients. Specifically, we need to be able to put patients into that tree and have them kind of drip down in the tree based on their age. Okay? Which is actually a far easier solution than have it alphabetically. If we had stored them alphabetically, that would be more difficult. But there actually is a way to do it with strings. You can do a lexicographic comparison with strings, and maybe we'll even look at that here in a few minutes. But let's build our tree first. So I'll create a new class, binary tree. All right. Okay, and just to clarify, so something else I saw in the assignments quite a bit is at this point we've learned stacks, we've learned linked lists, we've learned queues, but we've learned about writing them ourselves, not using Java's built-in links and stacks and queues and that kind of stuff. Does that make sense? Those guys require knowledge of generics to use them to their full capacity. And do we know what a generic is? Does anybody here know what a generic is out of curiosity? They're actually really cool. Just wondering if you knew what they were, since they were so prevalently used. All right. So, in any case, we're going to have a binary tree, and a tree is going to have a root, correct? And the root is going to be what? What kind of animal is the root of our tree? Binary tree? Okay. So we'll have a binary tree root. And then every binary tree has a left and right child, okay, which are also binary trees. Binary tree left, binary tree right. And we'll make all these guys private. Our constructor for this guy, and we'll say this dot root is equal to null, this dot left is equal to null, this dot right is equal to null. Just initialize the whole thing. We could make a display for this, but we might do that. Let's just keep going here. So we need to have a way of adding things to the tree, right? So when we say, so we're going to have a public, well, we can say void add, okay? And when we add something to the tree, the types of things we're adding to our trees here are patient records, right? Okay. Where does the payload get stored? Doesn't every binary tree have a value associated with it? So we need to keep track of the value associated with this guy. Do we actually keep track of a root? We keep track of the payload here. The root just happens to be the dude who's positionally at the top of the tree, right? All right, so we'll say private patient record. We'll call that guy the payload just to stay consistent. So we're going to add a patient record. So in here, we'll go ahead and set the payload equal to null as well. We might come back and modify that a little bit to fit our patient records a little bit better. But for right now, this guy's going to take in a patient record, PR. Actually, let's have it taken, call it the patient. I like that variable name better. First thing we're going to try to do is we're going to try to add it to this tree, right? Okay. We can add it to this tree if what's true? If his payload is null. Is that a true statement? If I can add it here, I should. So we're going to say if this dot payload is equal to null, this dot payload is equal to the patient. Else, I need to figure out which side it should go on. Should it go to the left or should it go to the right? If I'm in this else, that means that I know my payload has a value, right? My payload has a value. So what do I do when my payload has a value? Well, I have to look at the age, okay? So if the guy we're trying to add, the patient, has an age that's less than, do we do less than or equal to? That's what we do to the left?
Yeah.
That's fair enough, okay. So if the patient we're trying to add has an age that's less than or equal to the payload's age, we're going to add it to the left, okay? Otherwise, we're going to add it to the right. All right, and we're going to come back and modify this, I think, here in a few minutes. All right. So we're going to go to patient record. We need to teach this guy how to give us his age, right? So we're going to go ahead and we'll go to source, generate getters and setters, and all we care about is getting age. So we'll just get that one getter. So there's get age. All right, so now patient records know how to give us ages. So now I'll ask the question, if the patient dot get age is less than or equal to this dot payload dot get age, then add it to the left. Else, add it to the right. Okay? Now, as it stands right now, the first problem we have is that left and right might be null. I might not have a left and right tree. We certainly don't want to have a left and right tree if we're not going to put anything in there. Okay? So, we'll ask the question, if this dot left is equal to null, and this dot left is equal to new binary tree, then this dot left dot add. Actually, we can, yeah, that's fine, we'll do it here. The patient.
By the way, I think there's no need to write these methods now. Because if it is a null, it will determine based on itself. I mean,
if left is null, I can't say left dot add.
but you. Oh,
The payload will be null. We're implementing this a little differently.
okay, yeah,
Yeah,
different.
yeah. Because a binary tree by default has no payload, and he has no left and right tree. As of right now, we might decide to change it so he has a payload. But for right now, since he doesn't have anything, he's just an empty husk that we then add things into. What we need to do then is we need to check, well, if the payload we're trying to add should go to the left, well, can he go to the left currently? Is there a tree hanging off the left? There can be, but is there? If there isn't, make one. We made the tree. Then we added the value to the tree. Otherwise, there must already be a tree there. Go ahead and add the value. Make sense? Otherwise, pretty much the same code here for adding it to the right. If this dot right is equal to null, this dot right is equal to a new binary tree. This dot right dot add the patient. Else, this dot right dot add the patient. All right, so that's our add function. So these guys should kind of drip through. All right, so what we're going to do here at the very top inside of our driver is we'll go ahead and give ourselves, we actually don't even need an array. Let's just create a binary tree called the tree is equal to a new binary tree. And then in here, we're going to say the tree dot add. And what are we going to add? We're going to add a new patient record, rather. So we'll do that 100 times. All right, now if we want, just for, hey, sorry. So after this, the tree should actually have stuff in it, right? We don't know how to display a tree yet, but we should be able to run this. See, we have no errors. The tree fills up with stuff. All right, so now, after we filled our tree, we're supposed to get our smallest value, right? Okay, so smallest value should be the guy all the way on the left. So we're going to create in our binary tree, we're going to create a function, public patient record get smallest. All right, and this guy is going to say if this dot left is equal to null, return this dot payload. Else this dot left dot get smallest. And we return that. So that's get smallest. Okay, so when we ask our binary tree to get the smallest, he's going to ask, do I have a left tree? If I do, return his smallest. If I don't, oh, I must be the bottom of the barrel, so return my payload. Okay, so let's see if this works for smallest. So we're going to go ahead and we're going to say the tree dot get smallest dot display. And this should give us a young person, age 6. Fair enough. All right. So we should never get somebody younger than 5. Huh?
What does that?
I was clicking play too quickly. The virtual machine was having trouble shutting down.
Okay,
So.
because I was the one who tested that. I want
Yeah.
to keep clicking it.
All right, so that's that. Then public patient record get largest if this dot right is equal to null. Return this dot payload. Else return this dot right dot get largest. So that's our get largest. That should be a relatively old person. The tree dot get largest dot display should be late 80s. There's an 85. 85. All right. Seems legitish. All right, and then the root. The root's going to be all over the place, right? We have no idea what the value of that root node is going to be. Okay, because it's whatever number we generated first. Okay, whatever age we generated first. Could be old, could be young, could be somewhere in the middle. There's going to be no rhyme or reason. All right? So that's just get payload. Public patient record get payload. We could have used the setter and getter, the getter thing for it. We'll return this dot payload. And we'll go ahead and say the tree dot get payload dot display, like that. So 75, we should be able to run it multiple times, and the age should just be all over the place for that guy, right? All right, does that fulfill the assignment? All right, so not too bad. Kind of see why I did it the way I did it now. A little shortcut. Otherwise, had I not written it that way, get smallest and get largest would have been more difficult. These guys would have been a little bit more complicated.
Yeah, I'm using just using the left and doing while playing the
Yeah.
It's
All right, so,
I made it print them all from the youngest to the oldest.
okay.
I didn't know you want the youngest to the oldest. I thought all of them, but that way from the youngest to the root to the oldest to the top. Left.
Okay, so you did in order.
Yeah.
So
The
you,
top left, lower left to the root, and then the top right.
okay.
Print them all that way.
That's fine as long as you hit those guys. But the point of this was the lower left is the smallest.
Yeah.
Okay.
It goes
Yeah.
from the smallest
Yeah, I understand.
to the biggest.
I got it. Yep. Not my first rodeo. I got it. All right. So, but the one thing I want you to understand about binary trees is that getting the lower left is is the same as saying give me the smallest value. That makes sense? That's what it says. Give me the smallest value. Lower right, give me the largest value. All right, so this kind of segues us into this idea of searching. Okay, searching this stuff. All right, so having said that, and then the payload is just a crapshoot, right? That's just proving that you have access to the top of the tree somehow, right? It's really meaningless in the big scheme of things. But having access to it is important for where we're going next. All right, so let's talk about this. We got to add a couple of things here to give us some, we want to get some statistics about our, the depth of our tree. All right, so we want to know how deep is the left side and how deep is the right side. Okay, because right now in our mind we think of a tree as being kind of even, right? So the left side of the tree is kind of, you know, roughly the same size as the right side of the tree. Okay, but in reality we might have a freak show tree. Okay, we might have a tree that's 500 patient records deep on the left and like 3 deep on the right. All right, so that tree is not efficiently searchable. Okay, we're going to talk about ways we can fix that. All right, so let's go and give ourselves a way to kind of tell us what the depth is so we know, is it bad or not? All right, so we have to build in some stuff into our add method.
Screenshot of that output, the console, right? Just the output. The screenshot.
You want this?
No, you wanted us to just post this one also.
Yeah, screenshot of this and then your code, but the code's most important. Yeah, the most important thing to me is your self-assessment and then the code. Yeah, I mean, the output's nice, but the output is easily the least useful. Okay? That just kind of tells me, did your program work? But your self-assessment should give me an idea whether or not your program worked or not, right? If you say, look, I spent 14 hours on this, and A, B, and C works fine, but D doesn't work, which means that my program won't actually run, fine. So let me look at your code, and let's find out why it's broken. I mean, there were in the last assignment, there was somebody who I think gave themselves a self-assessment of a D, okay? And because they spent hours and just couldn't get their program working. Their answer was that it was a D because my program didn't work. Okay? I think I gave them 98. It was a one little stupid mistake they made, but they just kept overlooking it. That's fine. Okay, once they saw the mistake, they're like, oh, that was it? It didn't deserve a D just because it didn't run. They did a good program. And I might add, they actually used stuff that we've taught in class. I was very happy with that program, actually. I was thrilled with it. Okay, best non-running program I've ever graded. You know, so just because something doesn't run doesn't mean it's bad. Okay, not every program runs. Right? Every now and then I'm going to write stuff that doesn't run either. Right? Finding those errors are the important parts. Okay, and that's why the self-assessment is important to me. You know, I'm looking at your code anyways. You're not going to trick me and say, oh yeah, it works perfectly, there's no problems. And I look at this thing and it looks like it came through some sort of apocalyptic nightmare, right? You know, so if you ran into problems, tell me. So I can go and you focus me into the part of the code that you spent a lot of time on, and I can say, oh, this is where you went south. Okay, this is where the problem is. And if they had done this, and this part would have been easy. And they've proven to me that they knew how to do this part over here, but because they got stuck here, they never got to here. Okay, and I can now take that into consideration when I give you your grade. Right? If you just turn in somebody else's work, I can't do that. So, ay. All right, so we want to get the depth of a tree. All right, so what we're going to do is we're going to add a function here for our binary tree. Public int getDepth. All right, and this guy is going to return the depth of a tree. Okay, so this is where he currently lives. So we're going to actually let's call this let's do getmaxdepth. Yeah, max depth should be okay, but we might actually want to say get max left, get max right. Let's just write 2 of these. Get max left, get max right. All right, so get max left is going to say how deep is the left subtree. Okay, so we could ask if, and we're going to rewrite this here in a second, but let's just start with this. All right, so if, you know what, I want to rewrite it now. I want to do it the right way first. This will be more confusing. We're going to say get max depth. Every tree knows how to get a max depth. All right, so we're going to say int left is equal to -1. Int right is equal to -1. Okay, so by default, our left and right trees will be -1 depth. Okay. Then what we're going to say is we're going to say if, let's see, actually let's set both of these guys to, that'll make sense here in a second. We'll send them both to 1. So now we're going to say, because what I want to do here is I want to go ahead and if we have a left tree, let's ask him what his depth is, and we'll add 1 to it. If we have a right tree, let's ask him what his depth is. We'll add 1 to it. Because we have to add 1 because we're 1 level above him, right? Okay. Otherwise, if we have both, let's return the maximum of those 2 numbers. Okay? So, if this dot left is not equal to null, we'll say left here. I'm going to rename these to left depth and right depth. That way we don't get them confused with our this dot left. We'll say left depth is equal to 1 plus this dot left dot get max depth. If this dot right is not equal to null, then we'll say right depth is equal to 1 plus this dot right dot get max depth. And then we're going to return math dot max left depth, right depth. So see, just showed you a new trick. So the math class has a function in it called max that you pass it 2 integers and it returns the greater of the 2. Or you can just write an if statement that says if left depth is greater than right depth, return left depth. Otherwise, return right depth. So this saves us like 3 lines. All right. So for the record, if you ever use something like this in your code, even up to this point, I don't care. Right? I'm not nitpicking to that level. All right. I get it. Right? This is just a little convenience function or something like that. This isn't a deal breaker. All right. So this should be the max depth of a tree.
By the way, it means it will traverse all the tree, all the nodes.
Correct.
In the tree.
Yep, to give us the full max depth of a tree.
So it's not very efficient.
Well, that's a true statement. Yeah, it's not efficient to check the depth, but it's not as inefficient as it is to search a tree that's out of bounds.
Yes.
All right. So let's find out the max depth of our trees in general. So we'll go ahead and we'll say system.out.println, and this isn't going to give us a comparison of the left and right tree. All this is going to give us is the maximum depth. How many layers down does our tree as a whole go? So this doesn't really give us that much information, but it's the starting point of the information where we need to ask. Okay? Okay. Well, it's a starting point because we're just going to call it twice in a second here. So we'll say the tree dot get max depth, and this should tell us how deep this tree is. So 13, 18, 12, 13, 17, 16, 11. All right, so it looks like, you know, that maybe those 10s and 11s were probably relatively balanced trees if we were making a guess. Okay? If it didn't go down any deeper than that, we probably don't have one side that's too much deeper. But now we can ask, is a tree out of balance? Okay, so we're going to go ahead and we're going to, in our binary tree, we're going to say public Boolean is balanced. All right, and we'll end up making this private, but for right now we want to be able to call it conveniently, so we'll make it public. So for this, we want to get the depth of the left and the depth of the right, and they're going to start off as 0. So we're going to actually steal both of these guys, and you'll understand why here in a second. All right, and then we're pretty much going to steal, actually let's do, yeah, we got to do it this way. All right, so if this dot left is not equal to null, then we're going to say this dot left dot get max depth, and we're going to store that in left depth. If this dot right is not equal to null, then we'll say right depth is equal to this dot right dot get max depth. Now for right now, let's go ahead and print those two things. So we'll say system dot out dot println left depth is left depth. System dot out dot println right depth is right depth. And then finally, we want to return, let's say, left depth minus right depth take the absolute value of that. So if one side is 3, the other side is 2, 3 minus 2 is 1, or 2 minus 3 is -1, absolute value is 1. That's the difference in the depths of each one. Okay, and we're going to say as long as it's within 1, we're going to call it balanced. Now, some applications, as long as it's within 2 or even 3, we're going to call it balanced. And we'll talk more about that, but in general, the idea is that rebalancing a tree, which is where we're kind of going with this, is expensive. And since rebalancing a tree is expensive, we want to limit how often we rebalance that tree. Now, having said that, we can't just mix that up, change it up on the fly, because a tree that is out of balance by more than 2 will continue to be out of balance until we have recursively called rebalance multiple times on it. Okay? It's going to be more efficient if we rebalance it, knowing that if it's out of balance now, it's out of balance because of just the very last insert, the very last add. That's the guy that actually knocked it slightly out of balance. Make sense? All right, so we're going to return math absolute value of left depth minus right depth is balanced. We're going to say is less than or equal to 1. So as long as it's within 1, we're going to call it balanced. Okay? So now, let's go into driver. So now rather than printing out the max depth, we're going to say the tree dot is balanced So this guy has a left depth of 13, a right depth of 10. Not balanced, right? We're not printing out whether it's balanced, but it's not balanced. Here we'll print it out. System.out.println. All right, that's not balanced. Definitely not balanced. Not balanced. Ah, got a balanced one. Luck of the draw, right? Oi. Oi. Yeah, this is the apocalyptic freak show that we talked about here. This has a left depth of 15 and a right depth of nothing. That's called a linked list. That's what that's basically a linked list. Yeah, you could have some. You could have some. Well, no, actually, you know what? It would.
Because it's only 15 levels.
Yeah. You'll have some zags in there, but it's close to a linked list in terms of search efficiency. Yeah, so not very good.
Because the root was 85. Start from the biggest number.
Still out of balance. Still out of balance. Still out of balance. Still out of balance. All right. So at the very least, could we agree that being out of balance is a common state?
Yeah.
Okay.
Is it good to make the tree full? Fill the tree with all the tree with the elements with the.
Not before checking. No. Are you asking that? Like, should we fill the whole tree first and then find out if it's out of balance?
No. I mean, is it good to make the tree as filled as possible?
Make it as filled as possible.
Because we know that for balance, they have the same depth, but it's not filled. Some of the.
Yeah, I get what you mean. So you're saying, is it good if it goes outwards?
Mm-hmm.
Yeah, I mean, that doesn't really benefit you in terms of search efficiency because you're still always going down. So whether you go here or here didn't really, I mean, one of those moves didn't cost more than the other one.
For example, in the perfect situation for 100 records, it will have 7 in depth. Because.
I guess that's true.
Yeah, but so normally it's all like 10 or 12. So it means it's not filled. So it means actually we do want to search for one element, means like it will go like more likely be like 12 times other than 7 times.
Potentially, yeah.
Yeah, so it doesn't mean if it's a field then it is more efficient.
I suppose there's probably some truth to that, but I don't know if there's a convenient way of forcing it to be filled.
Yeah. And I guess in that case, maybe the insertion or the deletion will be less efficient.
Right, and the other thing that we'll find here is that one of the side effects of rebalancing a tree ends up being that your tree does get wide. Mm-hmm. Because we're going to rebalance it potentially after each add. Right, so right now we're kind of doing something that's unnatural, where we're filling the entire tree up, and then we're going back and saying, okay, how bad is it? Mm-hmm. Where in practice, what we're going to do is after each of these adds, it's going to see, did I just knock the tree out of balance? If yes, let me fix that by doing tree rotations before I finish this add maneuver. Okay, so an add might cost a little bit more at the cost then of searching that tree being faster.
Yeah.
That make sense? Okay. So now that we're able to find out whether a tree is out of balance or not, let's introduce.
What about you make the items instead of 100 like 200 or 1,000?
You mean the number of items?
Yeah. So you have 100 now. Let's see if we make more of all.
Yeah, I mean, it's not, it scales, I would think. And really, the fact that it's like this gives us an idea that our distribution of random numbers is relatively evenly distributed. You know, we're still at the luck of the draw for what the root node is, but generally speaking, yeah, so here's a root node. Let's find a root node that maybe is somewhere in the middle. Yeah, there. So with an age of 40 as your root node, it's pretty evenly distributed, values that are less than 40 and values that are greater than 40. So kind of proving our random number generator is at least adequate for this type of thing. I don't know if you'd want to use it for anything that required true randomness, but it's at least adequate for this. All right, so what I want to do here is we're going to look up AVL trees. And we're going to look at the Wikipedia article on this. This has some good charts for us. All right. So, and then we're going to actually do some of this. So an AVL tree is a tree that's self-balancing. So from our perspective, an AVL tree is a binary tree that guarantees that it's always in balance. So it has the extra step. Every single time that we launch there, every single time we add something to an AVL tree, after it's done adding, but before it returns from the adding function, it will check to see if that tree is out of balance. If it is, fixes it. Okay, so after every add, the tree is guaranteed to be balanced. Side effect is adds are more expensive now. So now we have to ask the question, do we want to use an AVL tree or do we not want to use an AVL tree? Well, here's the trade-off. If we're going to be searching our data much more often than we're going to be adding to our data, an AVL tree is awesome. Okay, a really good solution. If we're going to be adding to our data substantially more often than we're going to be searching our data, AVL tree is a terrible idea. Okay? Is an AVL tree then is a terrible idea, okay? Because we're adding too often. And an AVL tree is just going to be really slow for adding. And since we're not searching our data very often, who cares if the couple of searches that we do end up doing end up being a little bit on the slow side at the cost of the ads being fast. Okay? Where it becomes more of a coin flip is when we are kind of equally adding and equally searching. That's where we start having that wiggle room in the is balanced. Like, do we rebalance the tree all the time if it's outside of 1? Or do we kind of just say, as long as the tree's mostly balanced, maybe as if it's within 3. If it's within 3, then we say, okay, this guy's mostly balanced, let's not screw with it. Okay? We're going to still probably want to fix something where it was that 15-0. Okay, that's like our most recent Packer scores. At the end of the first half, at least.
1816. But against whom? The Lions.
I'm glad we lost.
With the Lions?
Yeah, I mean, well, at least after the game. I thought that.
Yeah.
I don't care about the winning or losing. It was their attitude when they gave the interviews after the game. I was pretty disappointed in the. I thought the Packers seemed like sore losers. I mean, they played a bad game. They played a team that they should always beat, right? But they did not play to beat that team. And the other team didn't even play great. They missed 2 extra points. NFL kickers don't miss extra points. They missed 2 of them. Okay, guys can go entire careers without missing an extra point. Okay, they missed 2 of them in 1 game and still beat the Packers. So, yeah, I didn't think there was a problem with the outcome. The fact is, we probably shouldn't even have had a chance to win at the end. Yeah. Okay. Fact is, if he hadn't missed those extra points, so the right team I think won, but I didn't like their attitude afterwards. So
I think they're gonna do the Vikings next time.
They'll probably win because at some point they have to turn it around. They're still favored. I don't know how they're favored over the Vikings. Vikings are ahead of them in the division.
Better than the Lions, I think.
Everybody's better than the Lions. Now, the ultimate thing is going to be if we lose to the Bears on Thanksgiving at Lambeau.
Chicago.
But we're in good company now. The Lions have 2 wins. Packers, the Bears. Those are the only 2 teams the Lions have beat. What's this? Football. Yeah, Milwaukee's baseball team is never good. We don't have to worry about that. All right. So in any case, Notice it says here's an example of an AVL tree. From our perspective, it's a binary tree, right? It's a binary tree that we just happen to rebalance as often as we deem fit. Where a generic binary tree, we would never choose to rebalance. That's not built into the algorithm for a binary tree. The binary tree algorithm just says stuff that's smaller goes to the left, stuff that's bigger goes to the right. That's it. That's the extent of a binary tree. An AVL tree is an example of a self-balancing binary tree. There's another version of this called red-black trees, which are similar, but we're going to deal with AVL trees here. Okay, so here's an example of kind of tree rotations. So is that clickable? No, that's fine. We'll see it down here then. Okay, so as an example, if the height of one side is greater than the height of another, so notice, let me actually zoom this in, see if we can get it. See that pretty good? Okay, so there's multiple cases. So right now we're asking a generic question. We're saying, is the tree out of balance? If the answer is yes, now we need to follow that up with how is it out of balance? Okay. Right now we at the very least know which side is too heavy, right? Think of it like weights. So we know if we're out of balance, we know that whichever of the left and right side is bigger, is heavier, that's the side that has the out of balance crap. Make sense? All right, so, but now we need to figure out which final side, left or right, is the actual side that's out of balance, because we handle our rotations, our tree rotations, differently depending on which of those sides is out of balance. All right, so this is called the left-right case. So the left-right case says if it's the left tree that's out of balance, but it's the right subtree of that tree that's actually the culprit, we do a single rotation. Okay? So that means we'll rotate the 4 up here and drop the 3 down. Okay, we'll see examples here in a second. Okay? So here's our left-right case. So we'll rotate up, which will give us the 5. Here's the 4, and the 3 drops down. So think of it like turning counterclockwise. All right? So we kind of grab the 3. Well, I guess you can kind of think about we're pivoting about the 3, but we're really dragging the 4 up, replacing the 3, and dropping the 3 down. Okay? But let's analyze a little bit more about what's going on here. All right, so when we rotate the 4 up, the 4 ends up being in this position. The 4 still has C as his right child.
Yes.
Okay, but what happened to C's
B.
left child?
B.
It used to be B, but instead, what do? We add B to 3. So we disconnect 3, we add B to it. So now B is the right child of 3. We don't have to explicitly add it to 3. To 3's right child, rather. We don't have to force B to be 3's right child. Is it even possible for whatever value B is to be less than or equal to 3?
No, there's no chance.
Because it's to the right. Because B is a child of 4. It's to the right of 3. So it's definitely a bigger value than A. By the structure of an AVL tree, right? All right, so this guy right here is guaranteed to be bigger, so we don't have to force it into 3's right child, because you know what? We could just say 3 add B, and we know it'll then just drop into its right child. We don't have to write a special function for it. We just have to remove B from 4 and add it to this tree here. Here's a tree, here's a tree. Take this tree's left tree and add it to this tree. Make sense? Okay. But before we do that, we had to rotate that 4 up. So let's think about that. How does that work? So how do I get the 4 to be here?
The 5 left pointer.
All right, so we want the grandparent here, this guy, to have his left node, because the left side is the heavy side.
Yeah.
We want his left node to be equal to his left node's right node.
Yes. And then
Make sense? Okay, and then we'll kind of fix it from there. All right, so question is, if a tree is out of balance and it's left heavy, what are we looking at here? Are we looking at the entire tree, or could we just be looking at the last 3 levels?
last 3.
Because all we care about is the very bottom of the tree. Because if we're checking to see if the tree is out of balance every single time we add something to the tree, we know whatever it is we just did is what the damage was. That's going to be at the bottom of the side that's heavy right now, right? So when we take this 4, we're going to rotate it up to here. That effectively says I need to traverse down my tree until I get to a depth that is 2 off the bottom. Okay? Because I need to have control of this guy, at least seemingly, right? So if I have control of 5, if I'm sitting right here, from here I can get 5's left child, and I can get 5's left child, right child. I can get those pieces. All right. If I'm here, though, as we currently have it written, we have no way of getting back up to 5. That make sense? So in order to complete our rotation here, we need to have 5, we need to have 3, and we need to have 4. We have to have control of those 3 trees. Because what are we going to do? We need to have a pointer pointing at this tree right here, because we're going to snap it off of this tree. Kind of hold it out over here. Right? Then what are we going to do? Then we're going to set this guy's left child to be this guy's right child. So we're going to snap the 4 off of there. So essentially what we're going to do is we're going to give ourselves 3 separate trees. We have the tree 5. We're going to break his left branch off. We're going to have the tree 3. We're going to break his right branch off. And then we have the tree 4. These trees are just floating there. Okay? But we need to keep them in order as to who was where. So since 4 is the left-right out of balance, that is left then right out of balance, we'll go ahead and add the 4 to the parent here. We don't need to set his left tree. We just add this tree as the child of this one. And he should just drop right there to the left. Okay? Then what do we do? Well, we needed to remove 4's left tree. Okay? Because this guy rotated left, his left tree is going to need to be reinserted into the tree. All right? So we'll remove 4's left tree, set that back equal to null. We know that this is the very bottom of the tree, correct? 100% of the time, this is the bottom of our tree. Okay? So we're asking after every single add. And if we're out of balance, we're out of balance at the bottom. Okay? So we'll go ahead and remove the left tree here where we know there's nothing below that. We'll re-add that to our 3. It'll drop into place. Then we'll add our 3 to the 4. Make sense? All right. So break them apart first to give us the separate pieces. Zeroing out the child nodes that we broke off. When we break 3's right node off, we're going to have a pointer pointing to 4, but 3 we need to set his right child to null. He no longer has a tree there. It needs to be prepared to receive a tree. Make sense? Okay, so if you think about this like a surgery or something, when we break this guy off here, we have to bandage the wound. All right? Similarly, when we break this tree off of the 5, we have to bandage that wound. So I have a pointer pointing at the 5, a pointer pointing at the 3, and the pointer pointing at the 4, and all those guys are completely separate from each other now. Make sense? They're no longer connected in any way. I broke those branches off when I noticed it was a left-right case. We'll talk in a minute about how we noticed it was a left-right case. Okay, so then what do? Assuming these guys are clearly broken apart, I can take this tree and add it to this tree. I don't have to do anything special, just add it. He should drop right in there to the left. That's the only place for him to go. We know he's going to go to the left because he used to live on the left. So we'll add this tree to this tree. Then what will we do? Then we'll add B to this tree. Then what will we do? Add this tree to this tree. 3 moves to get half the job done. Okay? Because in a left-right case, we have to do 2 rotations to fix this. So step 1 is what we just talked about there. Rotate this guy up, rotate that guy down effectively, right? Which leaves us with a tree that looks like this.
By the way, how we determine it's a left-right case?
Oh, we're getting there. Yeah, we're going to talk about that next.
We will do it.
Yep. Yeah, in just a minute. We're just about there. Okay. So right now we can just visually see it is.
Yeah.
All right. We'll figure out what algorithm we have to use to determine it. So after that first rotation, where we rotate the 4 to the left and drop the 3 down, our tree now looks like this. Would you agree if I asked if this tree was balanced, I'd get a false again? Like, I just did all this work. Okay? I just rotated a thing, and it's still out of balance. All right? So now my tree looks like this. Well, one thing we're going to see here is if the tree looks like this, we only have 1 rotation to make. So when we're in a right or a left-right case like this, our goal is to get it into a left-left case, not to rebalance it. All right? The final rebalancing move always happens from either a left-left or a right-right case. All right? So sometimes we have to massage our tree into a staging format. And I want you to think about that like in the creepiest way possible. All right. All right. So we have to get this tree staged into a left-left case before we can actually rebalance it. So if we're in a left-right case, our initial move is not a rebalancing move. It's preparation for rebalancing. All right. Then we go down. Now once we're in this position, which we know we'll be in, we don't have to check. Once we've detected we had a left-right case and we did that first rotation, we now can be confident that we have a left-left case. 100% of the time, that's what we'll have. All right? With a left-left case, then what do? We're going to take this in. So notice, in the balanced version, everything underneath the 4, the 3 subtree here, remain the same. So this guy doesn't change at all, right? The 4 almost doesn't change, except what? The C. And what do we do with the C? But we have to do this in the right order. We can't add it yet, because if we add it now, it's going to drop right back into place.
Yes.
Right? So if we know that C is greater than 4, but we also know that it's less than 5. Right? Okay, so if I take C off here and I just add it to 5 without breaking anything else, it's just going to plop right back into place. Okay, I just literally wasted my time. So what we need to do is give ourselves 2 pointers. 1 pointer pointing at the 5, this guy. Another pointer pointing at the 4, this guy. We know we don't need access to the 3 because the 3 stays put, right? Anything that's happening over there, it's cool. We don't need to think about it. All right, so 1 less node to think about in our 1 less tree to think about in our left-left case. So we'll break this guy off, setting this to null. We'll break this guy, so just that. So we have a pointer to 4 and a pointer to 5, and this link is gone. So then what will we do? We're going to go ahead and we're going to disconnect our C from our 4, preserve it. We're going to have to hold on to that. Okay? Then we'll add this tree to 4, which will drop it in here. We'll drop it to the right. Then we'll add the C to our tree, which should drop it to the right of 4 and then to the left of 5. Guaranteed. All right? So the important thing when you're writing this algorithm is never try to force something into the position you think it should go into. Just add it to the top of the tree that it needs to be added to and let it trickle into place. Okay? But the important thing is making sure that we're adding and removing things in the right order. Actually, removing things isn't all that important. You can do that. I mean, as we've talked about breaking things apart, that all kind of happens all at once, right? We just got just like crab legs, right? Just breaking the things apart, setting things to null, just staging it. But once we have our pieces, when we go to put it back together, the order is important. All right? Because we don't want to have something drop into place, into the wrong place because you did it in the wrong order. All right, so left case ultimately shifts into a balanced state like this. Similarly, right-left case, pretty much the same thing, right? It's heavy to the right side, but the right side is actually heavy to the left side at the lowest point, at the bottom, okay? Again, that's a hint, is everything that's happening here at the bottom of the tree. Everything that's happening at the bottom of the tree is where it's unbalanced. Okay? So what's our first move in a right-left case? It's to get it into a right-right case. It's about staging it. Okay, if we're in a right-right case, what are we trying to do? That's where we're rebalancing. Okay? So now let's answer your question. Your question was, how do we determine that a tree is out of balance? We've already done that. Now, how do we determine how a tree is out of balance? How do we differentiate between a tree that's out of balance in a left-right case versus a tree that's out of balance in a left case? They're both out of balance. We already got that nailed down. We can detect either of those cases as being out of balance. Good to go. But how do we tell the difference? If this is my tree, okay, let's just assume this is the whole tree here, okay? Even though this might as well be the last 3 levels of the tree. We already have the code that says this tree is out of balance to the left. We know that. So what we're going to do is we're going to traverse down this tree all the way until we get to the level right above the bottom. That make sense? And each time, we're going to go to the heavier side. We need to position ourselves. We're going to have to look at a larger example of this. So as I drop down here, how do I know I go to here versus here? What if I had something else that was over here? What if I had another subtree here and then another subtree off this guy?
Just compare the left and right tree, the depth of the left and right. If it's one.
As we're walking down the tree, we want to make sure we take the correct fork in the road. So as I'm walking down the side of the tree that's out of balance, each time I'm going to say, okay, I can choose to go left or I can choose to go right in a situation where it has both a left and a right child. We're always going to go to the side that's deeper, that has a bigger max depth, because that must be where the unbalance is. Okay? But at the same time, we also know how far down we have to go, how many decisions we have to make. And that's an important thing. If this tree here has a depth of 3, this tree here has a depth of 3, I know that I need to walk down to a depth of 2. Okay? Figure out how to get our pointers later, but I know I'm going to have to walk down to a depth of 2. So, a depth of 1 down off the top. So this is either 0, 1, 2, or 1, 2, 3, however you want to look at it. Doesn't necessarily matter as long as they move down to the right place. So from here, I'm going to say, my tree's out of balance. Where do I go? I go to the greater of depth. Is the left path greater than the right path? It is. So it must be out of balance to the left. And at that point, I've gone down as far as I need to go to make the next determination. Okay? When I know this tree is out of balance, I'm going to call a rebalancing algorithm. I'm going to start at the top of this tree, and I'm going to say, what is this tree's depth? In this case, the depth is 3. So I need to go down to depth 2. Getting to depth 2 will get me where I need to go to ask the question, is this well, is it out of balance to the left or is it out of balance to the right at whichever side it's out of balance? So right off the bat, I don't have to ask which side it's out of balance. I just have to say, enter the top of the tree here, take the fork in the road that leads to the deeper tree, which is going to be to the left. So right off the bat, we can mark down that at the very least, this tree is out of balance in one of the left cases, either left-right or left-left. We'll traverse down our tree all the way till we get to one level off the bottom, right here. And I ask them the same question here. Is the tree to the left deeper or is the tree to the right deeper? In this case, the tree to the right is deeper. That tells me now that this tree is out of balance in a left-right fashion. Make sense?
Yes.
All right. So, I answer which side is out of balance right at the very top of the tree. We might have a tree that's 200 deep, okay? 200 deep. But I can get this first part of this left or this right, with the very first question. Which subtree is deeper? The left one or the right one? If it's the left one, it's going to be one of the left cases out of balance. If it's the right one, it's going to be one of the right cases out of balance. Then what do? Then I drop down to the level right off the floor. One level up. One level up from the basement. All right. Once I'm there, then I ask my follow-up question. Is it the left subtree that's out of balance, or is it the right subtree that's out of balance? Make sense?
Yes.
All right. So that's going to give us the information that we need to determine which of these algorithms we have to perform. All right. So a left-left case and a right-right case are easier than a left-right and a right-left. We saw that already, that these two here only require 2 pointers. These guys here required 3 pointers to make it work. Okay? All right. So let's go ahead and let's see. Hold on. Do I want to take the break right now, or do I need to say something else? Let's at least ask the quick question, just so we can kind of go up to about 8. Let's find out if something is out of balance to the left or to the right off the bat. All right. So we're already asking is balanced. So let's go ahead and go in here to our binary tree. Here's is balanced. We're going to make this guy private. Actually, we're going to keep it public for now, just so we can test it outside of this guy. But we're going to actually ask this question inside of add. All right, so after we add something down here, all right, so right here, we are done adding. All right, so we're done adding there. Either we've just set the payload or we've added something to the left or right tree, whatever it is. We're going to ask if this dot is balanced. Specifically, we're interested if it is not balanced. If this tree is not balanced, we want to ask the question, is it balanced? Is it out of balance to the left or is it out of balance to the right? Okay? So if we're in this, that means we are out of balance. So we're going to say if this dot left tree. Now what's important about this, before I write this part. Geographically in our tree, where am I sitting right here? I just finished adding. The bottom of the tree.
Yeah, the bottom.
I'm where we just added,
Yeah, left.
right? As we go through this whole if statement, this is if-else structure, I'm basically at this level right here. The place where we finally were able to set the value. That make sense? So if you want, we can actually make it even more obvious. We can move that code right here. I just set the value. Now let's find out what damage we did. Wait a minute.
You cannot see if it's balanced.
Uh-oh. This doesn't tell me anything.
Yeah.
This dot is balanced is just going to add, in this case, this is the tree at the bottom of our binary tree.
The leaf,
It's this guy.
Yeah.
Okay?
you cannot tell anything.
If I just finished adding this 3, let's say, forget about the A and B, let's just pretend like this is the 3 I just added. If I just added this guy, I'm asking, is this tree balanced?
Yes,
100% of the time, he will be balanced.
there's
Because he's the bottom of the tree. At most, well, actually, he never has children.
yeah, so it's
This is the bottom.
Yeah, it is master balance.
This is it. Yes, I'm balanced. I have 0 children. Depth is 0. Or depth is 1, I guess we're currently returning. Okay. Balanced. Good to go. Don't need to rebalance.
So we cannot use this.
We always want to add. We always want to find out if it's out of balance. From the top.
Yeah.
How do we-
before add it.
How do we do that?
Can you go back to the code?
Maybe just to keep a variable to keep the root. I
Okay,
think
get back
you-
to the root.
I think you can keep. You have the root there.
Yeah, the root has to be set.
I don't have the root in here.
You have the root variable as a private variable.
Hmm.
Oh yeah. No.
So I need the root.
Where's the only place in our program right now where we actually have access to the root of the tree? The tree? Isn't that this is our big tree, right?
Yeah.
So the tree is the only guy that has access to the root.
Oh, yeah.
That make sense?
Yeah.
So when we make a call here to our binary tree to add something right here, we're going to go in to binary tree here, and we're going to go through this whole add algorithm. And this add algorithm is going to essentially traverse down that tree. It's going to leave the top of the tree until it can find the home for the patient record we're adding. Make sense? But wait a minute. I need access to that guy in order to ask where this tree is out of balance. How do I do that? How do I remember the top level?
Just the name of variable at the beginning of
Yeah.
the function.
The first, when there's no value in all, just say the first. How can we say that? Just say root equals.
Either to have a global variable.
Interesting. So global variable, somebody said they wanted to put it at the top of the function. Here, this function is going to get called multiple times.
No, not that function.
Which function?
Somewhere else and call it. Maybe a private.
Well, we do have some interesting things here. So we could keep track of a root node here. Because the only time new trees are born, other than out here, the only time new trees are born is when we didn't have a place to add it. If I can't add it here, let's try to add it to one of my children. A new tree is born right there. A new tree is born right here. Are either of these trees the root tree? Definitely not, right?
No.
These guys are definitely not the root tree.
No.
Okay, why aren't they the root tree?
We didn't have space in the tree and we added those.
The root tree is here. We only have one root tree. We only have one top of the tree. And that top of the tree is defined out here. So by definition, we know that anything in here is not the root of the tree. Is not the root of the tree. It's the root of its own little subtree, but it's not the root of the entire tree, which is where we need to ask whether something is out of balance.
Mm-hmm.
That make sense? So if I need to get access to the top of the root tree, what we can do here is I could have two constructors. One that knows how to build a root node, a root tree, and one that knows how to build a child tree. But then I still have the problem of how do I access the root tree? Actually, a pretty cool trick we're going to do. I'll let you think about it. All right, so let's take about a 20-minute break. Should I make a quiz when we come back on that?
No.
All right. So take about a 20-minute break, and we'll come back. And don't come bug me that you want to turn your assignment in again. So the answer is going to be no, and it's just going to tick me off. So.
I know what I'm saying.